Welcome to Module 2, The Chemistry of Malt. My name is Eric Steimel, and I can be reached at eric@hacking-beer.com. Beer is a fermented beverage made from a starch. We have our four main ingredients: water, malt, hops, and yeast. Should be familiar with these by now. There are other items that we can add to beer, but these are the ones we're going to focus on. Jim Leonard has already discussed water, and there are modules for hops and yeast. In this section, we're going to focus on malt, specifically some of the chemistries that are happening with malt. Malt is our starch supplier. It's our starch source. We can use corn and rice, but we're going to basically focus on malt. So the goal of brewing, obviously, is to make beer, but to do this, we need to convert that source of starch to usable sugars. This is started during the malting phase, and we finish that during our mashing steps. That sugar then gets converted to alcohol by the yeast during fermentation. Malt, well, what is it? Malt is a grain seed that's been allowed to germinate. This germination process is stopped through heating or kilning. This should have been covered in another module, and it's in the readings. Now, there's a lot of grains that can be malted: barley, wheat, oats, rye, etc. We typically focus on barley. There are two important barley strains for brewing: 2-row on the left, 6-row on the right. There are some visual differences here, but there's also some chemical and structural differences. If we look down this stalk of a 2-row, we see that it has 2 kernels, and likewise 6-row has 6 kernels. The starch to mass ratio in the 2-row is higher than that of the 6-row. However, the 6-row has more enzymes than the 2-row. Those extra enzymes are needed to help convert our starches from our adjuncts, such as rice and corn, into the sugars that we need. 2-row has more starch, but fewer enzymes. If you take a look at this link, the extra 2-row versus 6-row barley, there's some nice information there. Let's do a quick review. There's a steeping process. This starts the germination. The plant or the seed gets ready to grow into a plant. Enzymes are activated, specifically our alpha and beta amylase, which we'll discuss in a few slides. And this process is stopped through kilning. There's also some flavors and color that are added through the Maillard reactions. We've been using various words. We haven't really defined them. What is a carbohydrate, a starch, a saccharide, a sugar, etc. So let's start with carbohydrates. A carbohydrate is a compound that contains only carbon, hydrogen, and oxygen in the ratio 1 carbon, 2 hydrogens, 1 oxygen. Starches and sugars are carbohydrates. We can call or refer to sugars as saccharides. So a monosaccharide would be 1 sugar. It's the simplest of our sugar molecules. There's just one group. Mono meaning 1, saccharide meaning sugar. So it's a single sugar molecule. Polysaccharide, poly, many, saccharide, sugar. So that's many sugars. It's basically long chains of sugar molecules. A monosaccharide. This one here is glucose. Glucose is a 6-membered ring or a hexose, meaning it has 6 carbons bound to each other. We have them labeled here, 1 through 6. The formula at the bottom, C6H12O6, has that same ratio from the previous slide when we were talking about carbohydrates. Now this chain can undergo rearrangement and form a ring, or a cyclic version. You can see where the OH group is attached to the 1 That's that first carbon. When it forms the cyclic or the ring form, we get this OH group on the number 1. In this case, it's facing upward. So this is the beta glucose. Here, it's facing downward. So that's the alpha. Beta, batter up, alpha, down. This is the same molecule, we just have 2 different arrangements for it. There are 8 different ways for carbon, hydrogen, oxygen to come together in a hexose or a 6-carbon sugar. These are all isomers of each other. They all have the same chemical formula, but they have different chemical structures. They all have 6 carbons, 12 hydrogens, 6 oxygens. They're just arranged in a slightly different way. So we have glucose, galactose, and fructose. 3 different sugars, 3 different sweetness levels, behave similarly. They are isomers of each other. Each one of these can also undergo rearrangement to the cyclic or ring form. Like I said, these are all sugars. They have different sweetness levels. They're all monosaccharides. Let's introduce some common sugars. Glucose, basic food source. This is the basic sugar. Fructose, it's a fruit sugar, also found in corn. Galactose, it's a component of milk sugar or lactose. All 3 of these are monosaccharides. Lactose is a combination of glucose and galactose. It's a polysaccharide, meaning poly, more than one sugar, multiple sugars. And sucrose, this is our table sugar. It's glucose and fructose together. So how do we make a polysaccharide? Polysaccharide, simplest one would be disaccharide, meaning 2 sugars. So here we have 2 glucose molecules coming together. This is our 1 carbon. This is our 4 carbon. This hydrogen and this OH group are going to bond together. If we notice, this here is in the down configuration, so this is an alpha. Over here, we also have an alpha. These 2, H and OH, come together and it makes water. So here we are dehydrating this. We're removing a water and we're forming a 2-membered group, maltose. It's a disaccharide. We're bound between the 1 and the 4, so this is a 1,4 glycidic bond. This was in the alpha configuration. We can also have a beta configuration where this hydroxide is up. When it's in the alpha, we get maltose. You can see this one was down, we get a maltose. Over here, this would be in the beta, up. This gives us a cellulose structure. If we do this a 3rd time, we get maltriose. So it's a 3-membered chain of glucose. Glucose 1, glucose 2, glucose 3. And we can continue to do this. We can build, we can react and keep building out. We can keep building out. And that gives us amylose, which is a long, linear, helical sugar molecule, or starch, I should say, and amylopectin, which is a branched version of amylose. Here we have a series, hundreds and thousands of 1,4 glycidic bonds. The 1 carbon attached to the 4 carbon. Here we have the 1 attached to the 4, but we also have a 1 carbon attached to the number 6 carbon. So the amylopectin has 1,4 alpha bonds and 1,6 bonds. So the goal is to convert these starches to usable sugars. Glucose, maltose, maltriose, those are the ones that the yeast can easily ferment. So these are the ones we really want. We want highly fermentable sugars. We need enzymes to speed up this reaction. The higher the modification, the greater the amount of starch that is converted to sugars. Enzymes act as catalysts. They speed up the reaction, but they're not consumed. So we need to activate the enzymes, which act as catalysts. So what is a catalyst? Let's say we have this reaction. A plus B goes to AB. This would be very slow. If we add a catalyst, C, now we have A plus B plus C goes to AB plus C. This is fast. C is our catalyst. It speeds up the reaction, but it doesn't get consumed in the reaction. So once we convert to AB, we still have our catalyst, which can then be used to help speed up the reaction for other AB molecules. So what are our catalysts? What's our enzymes? Well, the first step in converting the starches to sugars is going opposite from what we had before, where we were taking these individual sugar molecules and making these long starches. The first step is hydrolysis. When we were putting them together, we were dehydrating. Now we're rehydrating, we're adding water. So during steeping, we're hydrolyzing these starches. We're adding the water back in. To speed up this reaction, we need alpha amylase and beta amylase. Alpha amylase is activated during the steeping process. Beta amylase is naturally occurring. Beta amylase is an exoenzyme. That means it only works on the ends. It's outside of it, so it works from the outside, exo. And it basically works on the non-reducing end of the starch. This breaks off two glucose molecules, making maltose. So beta amylase nibbles on the ends of these big starch chains and breaks off maltose molecules, which is a highly fermentable sugar. Alpha amylase is an endocatalyst. It works inside of it, in. It works inside of these amylopectin and amylose molecules. It's breaking off big chunks, say every 20 to 30, 40 glucose units. That basically gives us a soluble sugar, long chain of sugar molecules, which are referred to as dextrins. They're very sweet. They add a sweetness to our wort or our beer. But they can't be used by the yeast to form alcohol. They're too big. But now that you've broken this up, you're providing more ends for the beta amylase to attack, which will give us our maltose molecules. Kilning stops this reaction. All of this is happening inside the grain as we're steeping, as it's germinating. We're activating enzymes, and we're converting our starches over to sugars. As soon as we start to heat this reaction up, we deactivate, we denature some of these enzymes, and we stop the process. Also, we can add some flavors and color through Maillard reactions or Maillard reactions. We'll cover that in a separate module. So let's do a quick review. Steeping activates the enzymes, alpha amylase and beta amylase. Those starches that were present are broken down into smaller sugars. Kilning stops this enzymatic conversion and also adds some flavor and color. will post some suggested readings, and please feel free to contact me at the following email address for any questions.